Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Sunspots and Fury. Unveiling the secrets of solar storms. Our sun, a blazing ball of hot plasma, might appear tranquil from afar. But beneath its seemingly calm surface, a tempestuous drama unfolds. Violent eruptions and colossal blasts of charged particles erupt from the sun's atmosphere, impacting us here on Earth in dramatic ways. These outbursts are known as solar storms, and understanding them is crucial for protecting our technology and infrastructure from their disruptive power. While the sun provides the life-giving energy that sustains our planet, it can also unleash its fury. Solar storms are a stark reminder of this dual nature. These unpredictable events can disrupt our power grids, cripple communication systems, and even endanger astronauts in space. Predicting and mitigating their effects requires a deep dive into the sun's inner workings. The key to understanding solar storms lies in the sun's complex magnetic field. Unlike Earth's relatively stable magnetic field, the sun's is a dynamic beast, constantly in flux. This invisible force field, generated by the churning motion of electrically charged particles within the sun, constantly twists, stretches, and snaps. Dark, cooler regions on the sun's surface called sunspots are a manifestation of this turbulent magnetism. These sunspots are not merely blemishes. They are intense areas of magnetic activity where the sun's magnetic field lines tangle and erupt. Sunspots are often accompanied by intense flares and surges of energy, hinting at the drama brewing beneath the surface. The strength and number of sunspots can vary over time, following an 11-year cycle. Periods of high solar activity, with more frequent and intense sunspots, are known as solar maxima, while periods of low activity are solar minima. Understanding this cycle allows scientists to make some predictions about the likelihood of solar storms. Sunspots act as a trigger for the most spectacular solar events, solar flares. Imagine a colossal explosion on the sun's surface, releasing tremendous energy in the form of intense light and a torrent of high-energy particles. These particles, primarily electrons and protons, travel outward at incredible speeds, carrying a potent electromagnetic punch. A particularly powerful solar flare can unleash as much energy as 1 billion exploding hydrogen bombs. The light from a solar flare can reach Earth in mere minutes, causing auroras, northern and southern lights, in the upper atmosphere. However, the real drama for Earth unfolds with the next stage: coronal mass ejections, CMEs. These are massive clouds of superheated plasma, containing billions of tons of charged particles, that erupt from the sun's corona, the outermost layer of its atmosphere. CMEs travel much slower than the particles released from solar flares, taking days to reach Earth. However, they pack a much bigger punch, potentially disrupting our planet's magnetosphere, the protective shield that deflects these charged particles. If a CME collides with Earth's magnetosphere, it can trigger geomagnetic storms, which are the most significant threats to our technology and infrastructure. Our planet is not defenseless against the onslaught of solar storms. Earth possesses a natural shield, the magnetosphere, a vast region of charged particles trapped by Earth's magnetic field. This magnetosphere acts as a giant magnetic bubble, deflecting most of the charged particles unleashed by solar flares and CMEs. However, a particularly powerful CME can overwhelm the magnetosphere, causing it to shrink and distort. When this happens, some of the charged particles manage to slip through, interacting with Earth's atmosphere and triggering geomagnetic storms. A geomagnetic storm is a period of enhanced geomagnetic activity triggered by a CME interacting with Earth's magnetosphere. During these storms, auroras intensify, painting the night sky in vibrant colors. However, the real concern lies in the unseen effects. As charged particles slam into the Earth's atmosphere, they disrupt the delicate balance of electrical currents that flow naturally within it. These disruptions can have a cascading effect, causing problems in various technological systems. The consequences of geomagnetic storms can be wide-ranging, impacting power grids, communication systems, and even satellites orbiting Earth. Here are some of the potential disruptions. Power grid outages. The most significant threat is to power grids. The surge of charged particles can induce strong electrical currents in long power lines, overloading transformers and causing widespread blackouts. The severity of outages depends on the strength of the geomagnetic storm and the vulnerability of the power grid infrastructure. Communication disruptions. Navigation systems like GPS, which rely on signals from satellites, can be disrupted by geomagnetic storms. Radio communication systems can also experience interference, injuring communication networks. Satellite damage. Satellites orbiting Earth are particularly vulnerable to solar storms. The charged particles can damage electronic components on board, potentially disabling them completely. This can have a cascading effect on various services that rely on satellite data, such as weather forecasting, communication networks, and navigation systems. Understanding and predicting solar storms is crucial for mitigating their impact. Scientists around the world continuously monitor the sun using a network of telescopes on the ground and in space. These telescopes observe sunspots, measure solar flare activity, and track CMEs as they erupt from the sun's corona. Advanced computer models analyze this data, attempting to predict the trajectory and strength of CMEs and their potential impact on Earth's magnetosphere. While perfect prediction is still a challenge, these efforts provide valuable lead time for taking precautions and safeguarding critical infrastructure. Since complete prevention of solar storms is impossible, our focus lies on mitigation. Several strategies can be employed to minimize their impact. Grid upgrades. Power grid operators can take steps to strengthen their infrastructure, such as using special transformers that are less susceptible to induced currents. Additionally, early warning systems can allow for preventive shutdowns of vulnerable parts of the grid, minimizing damage and facilitating faster recovery. Satellite hardening. Satellites can be designed with shielding to protect sensitive electronics from charged particles. Redundant systems can be built into critical satellites to ensure some functionality even if parts are damaged. Communication backups. Communication networks can be designed with redundancy to ensure some level of functionality even if traditional methods like GPS are disrupted. Alternative communication channels, such as high-frequency radio, can be used as backups during geomagnetic storms. Solar storms are a global threat, and mitigating their impact requires international cooperation. Sharing of data from solar observatories worldwide is crucial for creating a comprehensive picture of solar activity. Additionally, collaboration on research and development of mitigation strategies can lead to more effective ways to protect infrastructure from disruptions. International organizations like the United Nations Office for Outer Space Affairs play a vital role in facilitating communication and coordination between different countries. The impact of solar storms extends beyond Earth. These energetic particles can disrupt the delicate balance of radiation around other planets in our solar system, potentially affecting the habitability of those worlds. Understanding solar storms becomes even more critical as we explore the possibility of life on other planets and potentially sending humans on missions to deep space. Studying the Sun's activity and its effects on our own planet can help us prepare for the challenges of venturing further out into the solar system and beyond.